Hello, good afternoon. Thank you very much, Dimitri. It's always a pleasure to be here in Natal. It's really very nice. Well, so let me start mentioning some people that are involved in this work. Here is me 25 years ago. uh, And so what I'm going to talk is about the topological phase transition, was here already the title. I'm not really a specialist in topology, neither in phase transitions, but in this area, I think I know a bit more. So I'll start with this very simple and intuitive concept of topology, né? And the idea is to be able to distinguish between a sphere and this kind of object here, that on the other hand, you don't distinguish between this one and this one. So there's this little joke. A topologist is someone that cannot distinguish between a cup and a donut. No? So, but this is clearly distinct from this other thing here. And I think this is quite intuitive. I don't need to apply to make use of any sophisticated concept for people to have an idea that these things are really distinct. So this is the definition of topology, that it's not a very sophisticated one, but it's the one you find in Wikipedia, for example. And what you can do with such a thing is to deform, to stretch, but you cannot break it. No? You cannot break this thing. In this sense, if you don't break, then you can deform, and these things become identical from the topological point of view. And here, the sphere is completely distinct from this type of phenomena here, this type of material. So in condensed matter physics, when we speak about topology, the object that is going to be deformed, let's say like that, it's the brilliant zone of the material. It's essentially, you have a K-space, you have the brilliant zone, and that's the thing that is going to be deformed. So we are always thinking in terms of brilliant zones. I think this happened before, no? It's not just... Yeah. So, well, this interest in topology and condensed matter physics is somehow related to this idea of the Majorana modes appearing in these systems, no? And these Majoranas, they are related. They are, like Karen was speaking, they are emergent particles in condensed matter physics. No, so this is not some basic particle as there is in, or as could be a neutrino in particle physics, but in condensed matter, this is an emergent excitation that is going to appear. And this appeared for the first time in, as far as I know, at least it started to raise interest, was in the work of Kitaev, that has shown that P-wave superconducting chains, they have a topological phase transition, and they present, in fact, two phases. One which is trivial, and from the topological point of view, you can distinguish this trivial phase by what we call a winding number. There is something like an order parameter for topological systems, and this takes a value which is W omega equal to 1 in the trivial phase, and then there is a superconducting phase also, which is topological, where the winding number presents this value -1. This is going to become clear as I'll show next, the Hamiltonian and what is the Kitaev chains. Né? But what distinguish is extremely important in this between these two phases is that the presence in the topological phase of these famous Majorana fermions that appear as emergent quasi-particles in this chain here. These quasi-particles that appear in the end of these chains, they are robust, they can and can be useful in several applications like qubits in quantum computers and so on. And this, in fact, has become the modern graal of condensed matter physics. Every lab that has the resources are looking to find these Majorana modes. And as far as I know, they haven't been found yet. So the problem to implement these ideas of Kitaev and to realize Kitaev chain is that P-wave superconductivity is rare in nature. Né? P-wave superconductivity is the normal BCS superconductor. The Cooper pair is a singlet pair. Né? So the two electrons get together with anti-parallel spins, forming a singlet state. So in real space, they have a wave function that is symmetric under the exchange of two electrons, but the spin part is a singlet which is antisymmetric under the exchange of two spins. And the P-wave is the Cooper pairs. They are formed with electrons with the same spin. So this is an S equal 1 pair of electrons forming an S equal 1 state, and you can have SZ equal to -1, 0, and 1. In this case, the wave function is antisymmetric in the real part of the wave function of the pair. When you exchange one electron by the other, the wave function changes sign, but the spin part is symmetric, and so the overall wave function of the two fermions becomes antisymmetric as it should be. So this type of superconductivity has not really definitely been observed in nature. Now, there are some candidates that have been thought to be triplet superconductors, but that's not really undisputable. No? So if you want to implement these things here, you have to have some idea of how to make a Kitaev chain being able to using the natural BCS singlet superconductivity or S-wave superconductivity as we refer. So let me show to you. Okay. So what I'm going to concentrate more here is in fact in the transition between the two phases, the trivial one and the topological one. This is a topological, refer to this as a topological quantum phase transition. It's quantum because it's a phase transition that occurs at 0 temperature. And the question is, what's the nature of this phase transition? I mentioned before the winding numbers, no? But the winding numbers, they have a value of +1 in the trivial phase and -1 in the topological phase. So if you think of the winding number as another parameter, you will think that this phase transition is a first order one, no? Because you have something like some kind of order parameter that is changing abruptly from one value to the other. But we see that is not really the case. And something very important also is that when you go from the trivial phase to the non-trivial phase in this topological superconductor, in both cases, either in the trivial or in the topological, you are always in a superconducting state. So there is no change in symmetry of the order parameter of the superconductivity when you go from the one phase to the other. So what's the nature of this quantum phase transition? This is really something which I think it's very curious, at least. Another point is that you cannot use the Landau framework to describe this quantum phase transition, these topological transitions, because there is no clear order parameter. No? You go from one superconducting phase to another superconducting phase, so the order parameter is the same in both phases. So you cannot write some free energy in terms of another parameter, because there's no order parameter between the two phases. So I think what is really got us into this problem was the fact that we were able to identify a diverging length in this topological transition. And this, for people that works in the critical phenomena, this is the characteristic of a second order transition. You have to have a correlation length, and this correlation length, it has to diverge at the phase transition. It's this feature which makes the system scale invariant at the quantum critical point, and then you need to, if you want, you have to have such a divergence of a characteristic length such that the system becomes scale invariant at the quantum critical point. So let me just show you here the famous Kitaev Hamiltonian. It's a very simple Hamiltonian indeed. It's an exactly solvable problem, because you have already done the BCS decoupling here. So you have a chemical potential, X is the position in the chain, you have a nearest neighbor hopping, and you have this Cooper pairing here, between electrons in different sites, X and X plus 1. And delta is the order parameter of the superconducting phase, which is antisymmetric in space. So delta ij is minus delta ji, and this is what is responsible for the non-trivial topological property. So when you can write this in the Bogoliub of the Gens form, you diagonalize the Hamiltonian, and you find the elementary excitations, and you find this sign K here, which is a signature of this antisymmetric pairing interaction. No? So that's the Kitaev Hamiltonian, and well, besides the Kitaev Hamiltonian, there are in fact other systems also which are topological and are even simpler than the Kitaev model. And they are in fact more easy to, let's say, if you want to prepare the systems, they are much more easy to prepare than P-wave superconducting chains that, as I mentioned to you, you cannot find in nature. So among these chains, which are topological insulating chains, there is a very famous SSH chain, and SSH stands for Su, Schrieffer, and Higger. This is a node model in condensed matter physics, a dimerized chain of carbons that models the polyacetylene. So these chains here, they are topological. They have two phases. One is topological trivial, the other is not. You can distinguish these two phases by widening numbers, and you can show that in the topological phase, there are some edge excitations which have very nice properties. Generalization of the SSH chain is the Rice-Meillet chain, which is different in the sense that you have a local energy on each carbon, which can assume values epsilon or minus epsilon and minus epsilon. So this is a more complicated, a bit more complicated version of this SA chains. And the other chains that we started to work with, which is the SP hybridized chains. So these chains, what it means is that you have a chain of atoms, and in each atom you have two orbitals, S and P, and these atoms, these orbitals in neighboring atoms, they can hybridize. And because S and P have angular momenta that differ by an odd number, the hybridization between these orbitals has to be antisymmetric. Or if I call this hybridization like Vij, I is an orbital on site A, I, and J the orbital, the other orbital, one S inside J and P inside J plus 1, VSP Ij is minus VSP Ji. So it is a well-known feature in chemistry and all of these chains. So this is the system that we are going to look more carefully. All these features that I mentioned to you before about the edge modes, they are going to show up in this type of chain also, with the addenda that they are more simple to realize in nature. A chain of carbon, for example, simple form of carbon in linear chain is a carbine. That's a new material that has appeared already sometimes in the literature. We know the sp3 carbon makes diamond, sp2 carbon makes graphene, and sp hybridization in carbon makes carbine, which are linear chains of carbon atoms with sp hybridized orbitals. So the Hamiltonian is very simple, is already a one-body Hamiltonian. The sp orbitals are very wide, so we can neglect, if Amir doesn't mind, we can neglect Coulomb correlations between these. So the Hamiltonian is again very simple. We have this local energy of the s orbitals, the local energy of the p orbitals, the hopping between the s orbitals, hopping between the p orbitals, and the hybridization between s and p. The way I wrote this Hamiltonian here already takes into account that the hybridization is antisymmetric, and this is a general property of this feature here, of the overlap of wave function between two orbitals. So this problem is it's like I have minus v and plus v between the orbitals in different sites, and in fact, this model can be mapped also in the SSH model. They are not really very different. Yes, VSP is equal VPS, but VIJSP is minus VJI. No. Well, wait. Well, actually, I'm not going to present the topology, how to calculate. But for this Hamiltonian here, it's very simple. You can simple winding number calculation is very is it's. I think that's the only one I know, I know to calculate. I'm trying to learn to calculate some Berry phases, but uh, I'm still complicated. But winding number, I know how to calculate. This is really simple. You write the Hamiltonian as H dot sigma using Pauli matrices, and then H you imagine as a magnetic field, and then you go from minus pi to pi in the Brillouin zone, and you follow the trajectory of the H. So there are two possibilities. Either it can come back to the same pole, or it goes to the pole. And this corresponds to two winding numbers, and this distinguish between the two phases. Yes, yes, and in this case here, I think it's safe to that this happens. So this model here, it has a topological phase transition. Whenever, let me come back here. I use the simplification here that the energy in the s orbital is minus the energy in the p orbital is equal to epsilon, and this model has a topological quantum phase transition when this thing is here is 1. And then you can calculate in the way that I pointed out. You can calculate and winding number. These two phases will be distinguished. The phase for epsilon over 2t smaller than 1 is the one that is topological. This is going to have a winding number which is -1. And the phase with this thing larger than 1 is the trivial phase with m equal 1. So, and then we are going to look a bit about the properties of these these phases. No? So let me first comment about the infinite chain. This is the Green's function of this very simple system. I have Fourier transformed and wrote the Green's function like 1 over z minus h. And then I have this Green's function here. The hopping terms, this gives this cosine, and the antisymmetric hybridization is complex. Actually, it's imaginary and has the sign of k over a, which is a feature due to this antisymmetric nature of this hybridization. So it has to be imaginary to preserve time reversal symmetry, and so it's written like that. So this you can immediately invert or find the poles of the Green function. The poles are the solutions of this determinant here that you use to invert, and the poles are the solutions of this determinant equal to 0. This gives essentially two bands. These bands, you can plot them as a function of k, and here is the band for epsilon over 2t equal 2 in the trivial phase. This is the band in the topological phase, and this is at the topological phase transition. The two bands merge with a linear spectrum here in the points where they merge. If you look at these two the dispersion relations, well, there's no evidence at all that one of these phases is topological and the other is trivial. Né? So when you look at the infinite system, it's very difficult. Then you have to calculate using this bulk boundary correspondence. You calculate either Berry phase share numbers depending on the situation, and then you'll be able, from the infinite, working in the infinite chain, you'll be able to see the distinction between the two phases. But if you look at this look as an insulator, né? The chemical potential is in zero, so these are two insulators, and cannot say, wow, this is topological and this is trivial. It's really very nice. Well, when you are working with the finite chains, then the situation is more simple, because then if you can actually diagonalize the problem, there's no many-body interaction. It's a very simple model. So you can set up a chain with 100 sites. You can go into Mathematica and you work a bit. For me, I had to work a lot, but then I was able in the end to find the wave functions of the edge modes in the first and in the last site of the chain. You are able to calculate the wave function at these sites. And what you find is that in this phase, where we call topological epsilon over 2t is smaller than 1, you find there are these edge modes here. This is for an 800 site chain. You see that the wave functions of the first and the last atom in the chain, they are extremely localized in the edge of these chains. So whenever you are in this topological phase, you'll find this edge mode here. If you go into the trivial phase, then you don't find these phases anymore. You don't find these features anymore. Here I plot the same wave function in an exponential exponential axis to show that the decay of the wave function inside the chain is essentially an exponential and has a characteristic length, which I called psi here. So this is the decay of the wave function of the edge modes inside of the chain when you are for a given psi, and I'm going to say what is this psi. When you calculate the eigenvalues also, you find zero modes appearing. You have the gap between the valence band and the conduction band, and you find that there are zero modes in the gap, and these zero modes are those that have this wave function here that appear here.
Because when you have an open chain, you can also have boundary effects even if you don't have a topological system.
Yes.
So to distinguish one from the other, because you could have the square modulus of the wave function and have some components in the boundary. But then you have like Friedel oscillation.
Yes, in
fact.
No, the envelope is always exponential, but you can have oscillations inside the exponential. So here's, if you see, there are a lot of, a lot of these steps here. So this is really an oscillating wave function, and the envelope is that is, well, so we have a topological phase transition here that I told to you, in the sense that for epsilon over 2t is smaller than 1, I go into Alixeia's review and I calculate the winding number there following his recipe. I find that for epsilon over 2t smaller than 1, I have a winding number that is -1, and for the other phase, I have a winding number that is +1. I go into my computer, use Mathematica, calculate for an open chain, and I find that indeed in one of these phases, I have edge modes that decay exponentially into the bulk of the chain. And then I come back to my question, what is the nature of this topological phase transition that occurs at epsilon over 2t equal 1? It's exactly the point where the gap closes and the spectrum looks like a Dirac-like spectrum. So what is the nature of this phase transition? And the question that I think is essential is that can we identify a diverging length in this kind of problem? And in fact, there is a diverging length. It's very easy to obtain because the distance to the transition is is epsilon over 1 minus epsilon over 2t. This is like t minus tc. That's a zero. It's a quantum phase transition, so there's no t. But this is the distance to the quantum critical point, which occurs when epsilon over 2t equal 1. So you can vary this parameter here and calculate the exponential decay of the wave function of the edge modes inside the bulk of the chain. And you can do that numerically. It's very simple. You make a simulation for different values of epsilon over 2t. You calculate the characteristic length, which gives the decay of the wave function. You find that this characteristic length depends on the distance to the quantum critical point, and furthermore, you find the dependence is that. So we have identified here a diverging length that occurs at the topological phase transition, and furthermore, we have determined a quantum critical exponent nu is equal to 1. And this comes out from these simulations in these open chains. Later on, I will argue, give some more strong arguments to tell you that since this is a quantum phase transition, there is a dynamic exponent in the problem, and this dynamic exponent takes the value z equal to 1 in this case. And this is, you can see this already from the fact that you are dealing with the Dirac spectrum at the quantum phase transition. And z is the power law of the dispersion relation at the quantum critical point, and omega is proportional to k to the z, and z is equal to 1 because the spectrum is Dirac-like. So that's what I wrote here. Now, this is the spectrum close to the quantum critical point. It's where the two bands touch and the gap closes. When you are not at the quantum critical point, there is a small gap. This gap vanishes with the distance to the quantum critical point. The critical exponents for the gap is the product nu z. And so when k equals 0, you have omega, the gap is, omega is proportional to the gap, and this gap vanishes with nu z. We have already found the nu equal to 1. We find that this thing is linear, and then you are able to determine both nu and z for this quantum phase transition. When delta is equal to 0, you are at the quantum critical point. The spectrum is linear in k. That's this type of spectrum. And then you get the z equal 1 independently from the thing. So we have identified the quantum phase transitions and already two quantum critical exponents, the correlation length and the dynamic exponent. We can also calculate, for example, you can use the chemical potential as the control parameter to approach the transition. You can identify epsilon with nu, the chemical potential. Then you can write the total energy, the ground state energy as an expression like that. Delta depends on the correlation length. And then you can calculate this integral here, and you can calculate the compressibility, which is the second derivative of this energy with respect to mu. And delta is mu minus mu critical, and then you get that this gives a log divergence for the compressibility. No? And who works with quantum phase transitions knows that there is a very important scaling relation. I call it quantum hyperscaling relation. And what this does is like a Josephson relation, but at t equals 0. The Josephson relation is 2 minus alpha is equal to nu d. Alpha in this case is the specific heat exponent. No? Here in this case, alpha is the singularity of the free energy. No? And you see that the dimension of the system increases because it's a t equals 0 transition. There's an effective dimension that is d plus z. And then if we plug alpha equals 0, which is generally associated with this type of behavior of the free energy, of the ground state energy here, you get alpha equals 0. Then if you plug this in the hyperscaling relation, you see that it's satisfied for this exponent. So you have here completely characterized the quantum phase transition without need to introduce another parameter, without need to use a Landau expansion. Just from the features of the transition, we are able to describe its universality class. We have 3 critical exponents here, and this is really enough to obtain. We could, for example, write the free energy of the system close to this quantum phase transition here at finite temperature, and we would know exactly what exponents would appear in the scaling form of the free energy. So this is really interesting because to describe a second order phase transition, you don't need another parameter, in fact. You can determine critical exponents and all that just from this type of thing.
Can't one define as another parameter the existence of edge states or not? Isn't that a good order parameter?
Somehow this is related to that, no? But to define is another parameter, because another parameter would the nice things about another parameter is something that is finite in one phase, goes to 0 smoothly at the phase transition, and then is 0 in the broken symmetry phase. And this is not really how this wave function behaves. So let's study a bit more the nature of these edge modes. So what I do is I return to my SP Hamiltonian, and I do the trick that was done for Kitaev chain also. And what I do is that I introduce some Majorana operators. What does it mean? I introduce creation and annihilation operator, and one is one is conjugate to the other, and the two are the same. So a Majorana excitation here means I have second quantized operator whose complex conjugate is itself. So I can write the electron operators for the s and the p electrons in terms of these Majorana excitations. Alpha plus alpha dagger bi is alpha bi. So these are really, they are real operators, and I can write the fermions as in this way here, in terms of 2 Majoranas. And then I can just write the Hamiltonian in terms of these new Majorana operators here. Then you do some algebra, you have to do a new set of Majorana operators. It's like you do a Bogoliubov transformation somehow. And then you end up with the Hamiltonian here of the SP chain written in terms of Majorana operators. So these gammas, they are all Majorana operators. The I is the site of the chain, and then V hybridization, T is hopping, and I have taken the chemical potential equals 0. So, in order to look at this Hamiltonian, it's still complicated, but you can choose, for example, to take V equal T and epsilon equals 0. Note that when I choose that, I am in the topological phase because epsilon equals 0 means epsilon over 2t is smaller than 1, so I am in the topological phase. When I take this, the Hamiltonian reduces to this equation here. That is, I took V equal T, epsilon equals 0, then I have basically this term here. So what is very interesting in this Hamiltonian is the following. You see, you start with I equal 1 to n minus 1. And you see that this gamma minus here is not, the gamma minus 1 is never going to appear in this Hamiltonian. Because when you start with I equal 1, you have gamma plus B1, gamma minus A2. So the gamma minus A1 never enters into the Hamiltonian. So in fact, these are the edge modes which appear in the system. They are Majorana excitations which have zero energy because they don't appear in the Hamiltonian, so it doesn't matter whether this excitation is present or not. The system, in fact, has a double degeneracy because either these states are occupied or not, you end up with the same energy. The difference between the SP Hamiltonian and the Kitaev Hamiltonian is the following. Here we have 4 Majorana modes. We have 2 Majorana modes in the beginning of the chain and 2 Majorana modes in the end of the chain. In the case of the Kitaev chain, you have only 1 Majorana in one end and another Majorana in the other hand. And how you see that? Just writing that Hamiltonian of Kitaev using this same transformation to these Majorana operators. But here you see there are 4 Majorana. This is an important difference between these SP chains and the Kitaev chain. When you write these end modes excitations in terms of the real fermions in the problem, you see that in fact you have in one end of the chain fermion, but which is not a trivial fermion. It's a hybridized fermion, a mixture of S and P states. And in the end of the chain, you have also an electron. So we don't have Majoranas in the end of the chain because these Majoranas occur in pairs. They combine to form electrons, but these electrons are not trivial. They are not S or P electrons. They are hybridized SP excitations.
The difference with the Kitaev chain comes because you took epsilon equal to 0.
No.
So because you already did a transformation, you didn't do anything, you didn't put any new term.
Yeah, no, the difference, for example, in this case, the Hamiltonian in real space is a 4x4, and in the Kitaev is 2x2. So that's the let's say mathematically, this is the difference. Yeah, because I think it's 2 orbitals in the Majorana. In the Kitaev is only 1 orbital. I think this doubling of the modes come because of the 2 orbitals, S and P. So these are the Majoranas. These are the edge modes whose wave function we detected in the simulation of the real chains. Now what I wanted to do how much time? 5 minutes? Well, I hope so. I can manage to that. So I come back here to the Kitaev chain now. That is simpler. And what I would really like to do, because I think all these scaling ideas, they become much more real, much more strong if you are able to do a renormalization group of this type of problem. Then you can really give some more basics basis, let's say, to this problem. And what I try to do is to use a method we used many years ago to apply a renormalization group to this Kitaev chain. And the idea was very simple. We have here cosine, and we have here a sine. Then we imagine that we have a chain with a length scale A, the distance between the atoms of the Kitaev chain, and then we do scaling transformation where we remove from the chain every other site in the chain. So now you have a new chain, which is identical to the previous one, but the length scale, instead of being A, now is 2A. So this is type of a very simple renormalization group for these one-dimensional systems. And the way to implement it, it's really very simple. In momentum space, when you reduce the lattice parameter, it's like you multiply the momenta by 2k. So this is the transformation here. K prime goes into 2k. And then you use the properties of sine and cosine, and you can see how the terms in the Hamiltonian are going to renormalize when you do this renormalization group transformation. And when you do that, this omega is essentially the hopping term here, and the delta is essentially the pairing. And when you do this transformation, because one is sine, the other is cosine, and you write sine of 2ka in terms of the sine and cosine, and then you obtain these two recursion relations here for the parameters when you do the renormalization group. And you can rewrite this thing in this very simple way here. Well, for those that are expert in chaotic systems, hi Alfredo, you recognize here immediately the logistic map, the famous logistic map. So you have this logistic map here, and you have, this is the renormalization of the hopping, and this is the renormalization of the coupling. And then you can study the fixed points of these coupled equations. The logistic map has two fixed points, two unstable fixed points. One is at omega equal 2. It has also a stable fixed point at omega equal -1. Whenever the modulus of omega is smaller than 2, and you iterate these equations, you are going to be always in the interval between -2 and 2. So this is a chaotic system. And when you iterate both equations, in fact, this is the phase diagram of the weak pairing phase of the non-trivial superconducting phase. And there is a strong coupling attractor also, because when you are out of the band, when your chemical potential is outside the band that goes from -2t plus 2t, you see that now the pairing renormalizes to strong coupling. It goes to an attractor at infinity, and you go out of the band, and then both omega goes to infinity, the hopping, the band goes to infinity, and delta goes to infinity also. And this is the strong coupling attractor that characterizes the trivial phase. This trivial phase in the Kitaev model is just the back limit of the superconducting model. In general, the BCS to Bose-Einstein condensation in superconductors is a crossover. You don't have a phase transition. Here, in this case, this crossover is exactly the topological phase transition. So in the non-trivial phase, you have a BCS like weak coupling BCS. You see that omega scales within that chaotic region. But as far as you go to the trivial phase, the omega and the couplings renormalize to infinity, and this corresponds to the strong coupling phase of back pairs, Bose-Einstein condensated pairs. So we can do some, we can transform these these things in a simple, all that space that I showed before where the omega and delta iterate, you can transform this into a circle, and then this mapping becomes equivalent to this. Sorry. Wow. Yes, this map becomes equivalent to that one, modulus 1. So this is how the angles renormalize along that circle here. But the thing is that you can calculate at this fixed point, you can calculate both the dynamic exponent, and you can calculate, you have the Jacobian of these two recursion relations here, and you can calculate the exponents at the quantum critical point, and then you find the values that make completely sense in this thing. Okay, I think that's what I wanted to talk.
Very good. Thank you.